Hello and welcome to all of linear regression, a quick video overview of really everything in linear regression. Of course, that's an absolutely terrible name because obviously you can't cover all of linear regression in a short video, which may be an hour, maybe more, don't know because haven't recorded it yet. Nevertheless, we obviously can cover everything. This video is really meant as a review of all the topics in linear regression that you should have learned or at least been exposed to over an entire 4 months of a university lecture course. Or you could use this presumably as kind of an introduction to a bunch of the topics or a refresher. Obviously, we can't cover everything, but we are going to go over all of the pieces very briefly. So let's get into the notes and see what's happening. Alright, so welcome to this lecture video. First of all, I'm going to call this all of regression, but I think that's actually kind of a terrible title. No offense to anyone who's used that title before. Instead, we'll just call it some of regression or an overview. Because ultimately, like I said, you can't really learn all of linear regression by listening to me talk for, say, an hour or so. In this video, you have to spend some time and really go through everything in detail. But we can still do a bit of a refresher and cover some of the main topics and some of the intuition that can come about in linear regression, which is quite important, right? So, where do we begin? Well, we begin with the idea of what is linear regression. What is linear regression? Question mark. Simply put, right? We have predictor variables. We have our predictors x, 1, say, through xp. We have our response variable, y. In this case, everything is a real number. Obviously, that doesn't have to be the case. You can get really fancy categorical variables, ordinal variables, vector valued, functional regression methods, time series, right? There's a million things you can do. For right now, everything is real valued. And ultimately, we want to figure out how does y depend on x? Seems simple enough, and yet there's textbooks and many textbooks written on it. In linear regression, the main idea is that we will be modeling y as a linear combination of the predictor variables x1 through xp. Most notably here, we have some unknowns, unknown parameters, beta. And of course, we have epsilon, which is going to be our IID noise. Now, the first thing you would note in linear regression is that the errors obviously in real data are not always independent and identically distributed, but it is a very nice assumption so that we can do a little bit of theory. And that is going to lead us into the main topic that you would first cover in linear regression, which is our least squares estimator. Because ultimately, we have to figure out what the betas are. These are the parameters that are going to tell us how y depends on x. What are the betas? Are they significant? What are they doing? Are they positive? Are they negative? Those are all questions we need to ask. But first, we have to figure out how to estimate them. And the most classical way to estimate them is the least squares estimator. The least squares estimator basically says, find the argmin, that is the beta. I think I was using beta tilde here in my notes. In p+1 dimensions, that is, we have an intercept 1, 2, 3 up to p. So we have p+1 parameters to try to estimate. And what we will do is minimize the sum of the squared error. What is that exactly? Well, it's going to be what we observe, yi, minus what we predict, y hat I, squared. And in this case, y hat I is going to be the ith predicted value. It's going to be effectively beta naught, beta 1, xi1. Oh, but we need hats everywhere. Everyone gets a hat, except the x's, of course. They're fixed. xip. So the idea, right, is simply we have a guess at what beta is. We can use that guess to then predict what y is. If we look at the difference between the y that we have and the y that we predicted, that's going to be a residual, right? And that model error, or residual, is what we're trying to minimize, or that is the squared error. If we were to visualize this, right, again, in 2 dimensions, when we just have a single x input and a single y output, we have a bunch of data points. As such, we fit a line. In this case, we get a slope and an intercept. And we try to minimize the squared error of the distance between each point and the line. So of all the possible lines that I can draw through these points, the least squares estimator is the one that's going to minimize the sum of the squared error, sum of these squared boxes. So it's pretty elegant, right? Why did they do it that way? Well, there's a couple reasons. One, it came about in the 19th century, and it sure is easy to take derivatives of quadratics, right? If you try to have a least absolute error, that's going to be kind of a pain to work with, right, if you don't have a computer. But we do get a nice closed formula, and we can show that this is equivalent to maximum likelihood estimate under the Gaussian distribution. So y least squares. Well, there are 2 reasons, as I noted. Well, there's probably more reasons, but the first reason is easy to compute. In particular, we have a closed form for our least squares estimator, which is going to be x transpose x inverse x transpose y. And this is, of course, for the linear model, y is equal to x beta plus epsilon, where what we have here is our response vector in n dimensions, our design matrix in n times p plus 1 matrix. We have our parameter vector, which is going to be p plus 1, and we have our errors, epsilon, which is going to be n-dimensional again. So we have our linear model, we have a design matrix, we have a least squares estimator. It's a closed form. It's really you're solving a system of linear equations in order to get it, right? That's a key point. Also, the least squares estimator is equivalent. Sometimes when you do math, you just can't spell right? Equivalent to the maximum likelihood estimator under Gaussian normal errors. Right? If you want to do maximum likelihood estimation anywhere in statistics, you need a likelihood. If you have to get a likelihood, you need a probability distribution, and we need to put a probability distribution on our model. If the errors are in fact Gaussian, then that means our response variable is going to be treated as Gaussian as well. If we try to do maximum likelihood, what do you find out? The maximum likelihood estimator for linear regression is the least squares estimator. So there is this nice tie-in with the normal distribution. Another reason why least squares is a reasonable thing to do. Furthermore, we get something very important, which is called the Gauss-Markov theorem. Not Makov, Markov. There we go. And the Gauss-Markov theorem is a very important result in linear regression. It basically says for the standard linear regression model, y is equal to x beta plus epsilon, if epsilon has, or well, we'll say has, and see if this English sentence makes sense. Mean 0. So there's no measurement bias or whatever in our errors. Homogeneous variance, homogeneous variance, i.e. the variance of epsilon I is equal to the variance of epsilon j for all I and j. That is, the variance doesn't change. Now again, in real data, you very often will have the variance changing depending on the inputs to your model. You could have regions of your sample space with high variance, regions with low variance. If we ignore that and assume that the variances are all homogeneous, the mean is 0, and uncorrelated, that is, the correlation between epsilon I, epsilon j is equal to 0, then beta hat, the ordinary least squares estimator, sometimes OLS is used as an abbreviation for this, is the minimal variance unbiased estimator. So that's cool. I mean, presumably, right? What does that even mean? It means that of all the possible unbiased estimators for beta hat, that means their mean is actually going to be beta. Of all of them, the least squares estimator has the lowest variance, and therefore it is, in some sense, the best one to use. Now, that doesn't mean there's not other biased estimators that can do even better. Think things like ridge regression, lasso, more modern techniques. But when it comes to unbiased estimators, really the least squares is the best you can do in the sense of minimizing the variance, which in this case would be equivalent to minimizing the mean squared error because the bias would be 0. All right, well, we're not going to derive that as I do in my notes because that's going to take too much time, and we're trying to do all of linear regression in one video before my voice gives out. So let's see what else we have to talk about besides. So in statistics, you basically do 3 things. 3 things in statistics. Number 1, estimate. Well, I just did that up above. You estimate things / fit models. Calculate parameters that, seem reasonable. But then step 2, hypothesis test. That is, are the fitted parameters actually any good, right? I mean, I can fit a model, sure, but does it actually matter? Is it actually important? Does it have any significance to it? That's kind of step 2. And step 3 is kind of prediction / forecasting. We might want to know how well can we predict new values, how well can we use this model for some type of prediction or inference problem. Anyway, we just did number 1. That's up here. Now we can do number 2. That's going to be down here. And in linear regression, we can have some very nice hypothesis tests if we assume the errors are normal. They're not always normal, but if we can assume that, then we get some nice test statistics out. So if, big if, epsilon is normal, 0, sigma squared, unknown variance, but homogeneous, uncorrelated, right? All the conditions of the Gauss-Markov theorem are satisfied by saying this. But note, the Gauss-Markov theorem does not require normality. It just requires, again, mean 0, homogeneous variance, uncorrelated errors. Right, so given all of that, what do we have? Well, we have this setup. We have that the epsilons have a normal distribution. What does that mean? That means that we can get goodness of fit tests. Basically, how well does the regression fit the data? And the main one that we use in classic linear regression is called the Ftest. I think F is was given because of Fisher, right? Sir Ronald himself. But oftentimes you will, not often, but every so often you will see somebody refer to it as Snedecor's Ftest, who was a, I guess, less famous statistician than Ronald Fisher, who, takes a lot of the credit. But he did a lot of cool stuff too. And a lot of terrible stuff, but save that one for another day. Anyway, whenever we do a hypothesis test in statistics, we need hypotheses. And what we have here is our null hypothesis. Our null hypothesis is that none of the parameters have any effect, or I should say none of the predictor variables, x1 through xp, have any effect on the response. As a result, what I'm saying is that all of the slope parameters, beta 1 through beta p, they're all 0. So, right, x times 0 is 0. Now, our alternative hypothesis is going to be the logical complement of that. What it is it's that there exists a beta I that's not equal to 0. So at least one of those parameters is non-zero. So at least one of those predictor variables is actually giving us information about y, is actually doing prediction, right? That's the main setup here for the Ftest. Now, the Ftest statistic is going to be a ratio of sums of squares. The global Ftest is going to be the explained sum of squares divided by the p parameters it takes to, I guess, get that explained sum of squares, divided by the residual sum of squares. Now, this is roughly saying this is the variation in y explained by the model, and the residual sum of squares is the variation in y not explained by the model, the regression model, just to be clear. Right, so you fit your linear regression model, it explains some amount of the variation, that's the explained sum of squares. Everything that's left over is the residual sum of squares. So they have this kind of complementary effect. The total sum of squares, the sum of them is going to be the total variation present in the data y. So what do? We compute this thing. If we have a normal distribution, then this has an F distribution. Snedecor's F, we can call it, with p and n minus p minus 1 degrees of freedom. What we're kind of doing here is we're comparing two different statistical models. We're comparing the intercept-only model, which basically says y is a constant plus noise. Okay, that's boring, but that can be the case, right? Versus the full regression model, which is y is an intercept plus a, I guess, linear combination of predictor variables plus noise. So really we're saying is, does this linear combination of predictor variables matter? Now, we can get a little bit fancier, of course, and dig down into individual betas. Because the first thing you notice, well, okay, if I reject my null hypothesis here for the Ftest, I'm saying that at least one of the betas is significant. Which one? Don't know. We have to come up with a new statistic for that. And that's where the t-test comes in. So if we actually want to know which of our betas is significant, we do a t-test on each one. Our null hypothesis is that beta I is 0. Our alternative is that it's not 0. Again, this is saying that the beta basically we're saying, is xi influencing yi in any way? And it's influencing it through beta. Anyway, in the case of this, what we're going to do is we're going to estimate beta hat. I mean, what we're ultimately doing is we're saying, well, beta hat I minus 0. Again, we're always working in the null hypothesis setting when we write a test statistic. So here we have our test statistic t, and it's going to be beta hat I minus 0, but we need to normalize it. So beta hat is going to have a normal distribution because we assume that the errors are normal, but right, we don't know what the variance is. We don't know what sigma squared is, so we estimate it. Whenever you estimate the variance, you're going to be switching from a normal distribution to a t distribution. Mainly because the estimate of the variance is going to be chi-squared and independent, et cetera, et cetera. You know, we can spend, well, what, 32 classes talking about this stuff. That's not the purpose right now. Though, hey, maybe if I have some free time, I can actually turn this entire class into a set of videos too. But seeing as how COVID is, I guess, over, or at least lockdowns are over, right? Ain't got the time for it, sorry. But hopefully this will be helpful for my actual students who should be studying for their final exam right now, assuming you're watching this after I just posted it. Anyway, we do the usual thing, right? You compute your t statistic, you compare it to a t distribution with degrees of freedom based on the residual sum of squares, and then you say, well, is it significant? Is it not? Is beta I, is xi influencing yi through beta I or not, right? What is the effect size? Things like that. Anyway, moving on, we can do things like partial Ftests and confidence intervals. These are all quite nice topics, right? We can also compare nested models, nested linear regression models. That means that one model has more parameters than the other, or it has the same parameters and additional parameters, right? One model is a simpler version of a different model. So we can also compare nested models using an Ftest. And roughly what it's going to look like, again, without going into the horrible mathematical details, it's going to look like the numerator, which is the change in the sum of squares divided by the change in the number of parameters divided by, well, the residual sum of squares for the full model divided by the total number of parameters. So what I mean by this is that in the numerator, we're looking at how much did, well, two things. The residual sum of squares decrease when I add more parameters to my model. Equivalently, how much did the explained sum of squares increase? These are optimization problems, and if we expand our optimization space, the minimum can only get more minimized, and the maximum can only get more maximized. But we have to know if increasing the explanatory power of our model, if increasing the explained sum of squares is justified by adding all these extra parameters into our model, or is it just a bunch of junk, right? That's basically what we're saying. If I want to add 5 more predictor variables into my model, did the explained sum of squares go up enough to justify that, right? That's what we're trying to do here. And the denominator is just going to be some estimate of the variance, because we always need some estimate of the variance to get our denominator. Anyway, this is also going to have an F distribution. The degrees of freedom are going to be based on the change in the number of parameters. Now, for my bullet point number 2 up above, right, where I said we can do estimation first, then hypothesis testing. There's a dual aspect of hypothesis testing, and that's confidence intervals or regions. So what we have there is that for any of these hypothesis tests, we can also try to construct a confidence region for our parameters. I'm not going to go into details on this because, well, it's kind of the same thing as the t-test and the f-test. It's just that now we're going to be constructing an interval in the case of the t-test and an ellipsoid in p plus 1 dimensions for the entire vector beta if we want to do that. So I'll say confidence regions. Right. In this case, if you have an estimated beta hat somewhere in your p plus 1 dimensional space, what you can do is you can draw, or you can construct a confidence ellipsoid for it. We'll call it the 95% confidence ellipsoid based on the F distribution. And similarly, right, what we could do is we could do the same thing for an individual beta. We could ask beta hat I minus beta I less than or equal to, well, some number times the square root of the standard error is usually the square root. So we'll just say some number times the standard error. Right, and then what are we saying when we have a confidence interval? We're saying that the probability that this random data-driven interval contains the fixed true parameter that we're looking for has probability, say, 95%, 99%, 1 minus alpha percent, whatever you want, right? It's always good to remember that as a frequentist statistician, right? No Bayesians at the moment. We treat beta as a fixed but unknown parameter lying somewhere out there in, say, p plus 1 dimensional space. The estimate is random, and the confidence interval or ellipsoid or region constructed is also random. It's determined by randomly sampled data. So it's always good to remember that, right? Because it's something very easy to get messed up with. All right, well, that was a horribly rushed introduction to linear regression. But again, hopefully you've already seen some linear regression before watching this video. Otherwise, it's going to be kind of a shotgun blast of all this information. So the next thing I want to talk about is model assumptions. Because linear regression is all well and good when you're in the, I guess, utopian mathematical world. Right? When everything is IID and Gaussian and everything's perfect, great. That's wonderful. But in the real world, that's usually not the case, right? You're going to have some messy variance issues. You're going to have model selection problems. You know, you're going to have correlations in your errors, right? There's lots of trouble that can come about. One way, a very good way, to try to get a sense of, you know, does my data satisfy the assumptions of linear regression? Right? If we want to know if the data satisfies these assumptions, well, there's many different tests and tricks and plots we can use. One thing that's super useful is look at the residuals. Residuals, right, are model errors. They're going to be the observed value y minus the fitted value y hat. But even furthermore, going slightly further, we can look at the so-called studentized residuals. So this will be look at the studentized residuals, where, of course, we call them studentized residuals because of student's t-test, which is just William Seeley Gossett hiding his name, the guy who came up with the t-test. I think I've said this probably many times before, but he worked for the Guinness Brewery, and he wanted to keep his trade secrets, I guess. So he published the t-test anonymously under the name Student. I don't even know if that counts as a name, but whatever. And thus, the word student shows up everywhere now in modern statistics. Whenever the t-test is there, like student's t-test, studentized residuals. Like, great. Thanks, Gossett. But the t-test is pretty cool, so I guess I should thank him with all sincerity. Anyway, what we do with the studentized residuals is we take our regular residuals and we divide by an estimate of the variance. So we standardize by an estimate of the variance, well, the square root of the variance, obviously, right? The variance, the standard error, standardized by an estimate of the variance of Ri, where here we have our residual sum of squares, that's the total sum of the model errors. We have our degrees of freedom here, and we have this crazy thing where P, sometimes referred to as H, the hat matrix, is going to be an orthogonal projection, which is going to take our noisy data and project it into our model space. And I minus P is going to be our orthogonal projection, which kind of projects into the space that is orthogonal to the model space. It's kind of what our models can't tell us, in a way. Turns out linear regression is actually just linear algebra, that subject that you learned and you thought, man, this is kind of boring. It's actually super cool, super useful. I'm going to draw a picture, and it may or may not make sense. Anyway, you can imagine your response variable y. Y is an n-dimensional vector living in, well, n dimensions. It's noisy. It's a signal plus a noise. What we do is we have, in some sense, maybe I should change the color on this. We'll do green for model space. And we'll do red for residual space, the orthogonal space to the model space. Ultimately, what happens, right, is our so-called P or hat matrix is going to, well, shove a hat onto Y. When we apply it to Y, we project into a linear subspace. That linear subspace is going to be P plus 1 dimensional, assuming that we have P predictor variables and one intercept term. Our residual space is going to be the orthogonal projection, which in this case is I. Well, I'll just write it over here like I did for the other one. The residuals, which is I minus, well, I'm just going to write P because I don't really feel like writing X, X transpose, X inverse, X transpose again. Yeah, and then the dimension of this space is going to be the complementary dimension. See if I can erase that without killing my axis. N minus P minus 1. So again, that's what linear regression is really doing. It's saying I have a P plus 1 dimensional linear subspace. Well, that's spanned by the columns of my design matrix. I'm going to project onto that. I'm going to take my noisy data and turn it into a model by projecting onto that space. The complement, or the orthogonal projection, is going to take us into the space orthogonal to our design matrix. It's everything that we kind of can't get, and it's basically where we're shoving our noise. We're really just separating a signal from a noise here, a signal in green, noise in red. It's one way to think about this. Anyway, that was a really circuitous way to say the residuals have a variance based on 1 minus p, where p is this hat matrix or projection matrix. And we can use that to standardize the residuals, to get studentized residuals. And then we can, to continue this train of thought, we can ask, are any SIs particularly large? Big. Maybe I should put an absolute value here just to indicate that it could be very big positive or very big negative. If we have a very large studentized residual, it indicates we might have an outlier in the y direction, the horizontal or the vertical direction. The idea being that we have a point that's really high above or below the regression line. And I guess when I say regression line, I mean regression hyperplane, but, you know, a regression line is fine. Anyway, plotting the studentized residuals is very useful. It's something that happens in R in a lot of the default plotting for linear models. You can also plot residuals versus things like fitted values, because sometimes the fitted or the predicted value is going to have an effect on the residual. If we don't have that homogeneity of variances, if we have heteroscedastic variances, then the response might be somehow linked to the variance of the residual. It's kind of subtle when I say it like that, but it's also kind of more obvious in real data, where depending on your inputs, you might just have a lot noisier observations than other inputs. So that's something we can look for. Another plot that is sometimes useful and sometimes just, you know, annoying to look at are the so-called normal QQ plots. QQ for, I guess, quantile versus quantile, probably. Anyway, the QQ plots, if you ever plot them in R, you're going to get something that looks like this, where you have some data points that maybe look like that, and then you get a straight line or a diagonal straight line. And the question that a QQ plot is asking is basically saying, do my standardized, or maybe studentized, I should say, but I'll just say standardized residuals look normal-ish? And when I say normal-ish, I mean literally, do they look like they're coming from a Gaussian distribution? Because in a weird way, the residuals are kind of like we're estimating the errors. Now, that's not exactly right, but intuitively, there is some reason to think of it kind of like that. And our errors should look Gaussian, and our Gaussian distribution is very nice bell curve. Do the errors or the standardized residuals actually look like they're coming from a normal distribution? Yes or no? Well, it's hard to really say, right? You can get one of these QQ plots, and if the bulk of the data points are lying on a diagonal, what you're basically saying is the mass of the distribution looks roughly normal. Oftentimes when you do a QQ plot, you will see some deviations in the tails. That's perfectly reasonable because oftentimes you do have the occasional weird outlier point. I guess my point is that if you look at a QQ plot, you don't need every data point to lie exactly on the diagonal to claim that it's normal, but you know, you can still try to gain some insight based on those. Anyway, moving right along, sometimes your data isn't linear or doesn't have homogeneous variances. Because when you write down a linear model like you do at the very beginning of this lecture, right, it's this very idealistic thing. the model is the right answer. It is that our data, our response variable y very much is going to be a linear combination of the x's, a signal, plus some homogeneous noise epsilon. Now, in the real world, that's not often the case. You might have some strange logarithmic relationship. You might have a polynomial relationship between the inputs and the outputs. And of course, the variances, as I keep ranting about, may not be homogeneous, which is something else we would have to take into account. To do that, we can try to transform our data. So we can try transforming x and or y. But we have to be careful when we do that, because when we transform our data, one is we're changing the what is linear, right? But we're also affecting the variance. And this leads into the idea of variance stabilizing transformations. The idea being that if I were to, say, replace y with, say, the log of y, I do a logarithmic transform, then the variance is changed. Maybe for the better, maybe for the worse, but the point is it is going to change things. When you start transforming your variables, you're going to also be transforming the variance. You can't really transform y without affecting, one, is it linear in x or not? And two, what is epsilon doing? So, for example, we could try a model like y is equal to beta naught plus beta 1 x1 plus epsilon. We could also try a model like the log of y is equal to beta naught plus beta 1 x1 plus epsilon. Is one better than the other? Well, no, because there's absolutely no context here to determine which one would be a model we should use. But it is worth noting that you can, for example, look at fitted values versus residuals to see if the transformed model looks linear and homogeneous in the sense of the variances. Now, of course, if it's just a simple regression with one input and one output, you can just plot the data, x on the horizontal, y on the vertical. What does it look like? Does it look reasonable? But if you're working in p equals 10 dimensions, or 20 dimensions, or 100 dimensions, you can't really visualize that so well. So what you can do, rather than looking at input versus output, you would look at fitted versus residuals. And by looking at fitted values versus residuals, you can say, well, does it look kind of flat? Like for every fitted value, we have roughly an independent IID residual noise. That's what we'd want in a linear regression context. If you plot your fitted versus your residual values and you get something like bowl-shaped or something like with some strange pattern to it, it means there's probably more work you have to do with respect to transforming your data to get a better fit for your linear regression. Right. What else? Oh yeah. Fun little side note. If you aren't sure how to transform your data, because it's not always obvious, right? There's so many things you can try. Then see something called the BoxCox Transform. And BoxCox is basically a data-driven transform. I mean, strictly speaking, I guess doing a log or something transform would be data-driven, but you actually have to stare at it with your eyeballs, right? And say, does this look better or worse than not log transforming? BoxCox takes the data in and tries to estimate a power transform. Basically, it tries to roughly, there's a little more math involved that I'm not going to write down here, but roughly replace y with y to the lambda, where lambda is chosen from the data. It's a super useful technique because, you know, you might think, well, do I want to take a square root of my data? Is that a reasonable transform? Do I want to take a log, which is roughly when lambda is equal to 0? Again, brushing over all the details, but they are in my typed lecture notes, of course, and maybe for some future endeavors, but it's useful because it allows the data to kind of decide where it thinks, how it thinks it should transform y, at least with respect to taking it to a certain power. Do I want to square it? Do I want to square root it? Do I want to invert it? Do I want to log it, right? All of these kind of come in to the BoxCox transform, so it's quite a useful tool to use when you're working with real data. So we'll highlight it in yellow, just because I think it's kind of neat. Otherwise, that is rough. Oh, yes. There's other things we can consider, which is, right, if we're considering a transform of y, we can also consider things like polynomial regression on x. So, right, rather than just saying y is equal to, or let's say y, yeah, we'll just say y is equal to beta naught plus beta 1 x. We could keep going, right? We could have a beta 2 x squared, beta 3 x cubed, and so on. And then eventually have an epsilon for errors. Now, in practice, you never want to do that because, well, there's a problem with shoving in all these polynomials in this form, and they're all highly correlated with each other. That's going to be something called multicollinearity, which I'll mention in a minute. But I will put a side note. Probably better to use orthogonal polynomials. And probably, I always say probably because there's never any hard and absolute rules, right? But probably shouldn't use high degree polynomials. In a weird way, polynomials actually fit data too good or too well, whatever the correct English is, I don't know. The idea being that, right, if I have, let's say, n data points, I could take an n plus n minus 1 degree polynomial, and that line will magically go through every single data point exactly. The problem is I've just overfit drastically to my data, right? We typically don't want a regression line that's going to pass through every single data point. That's not the idea. The idea is that we have a simple, low-dimensional model and then a whole bunch of noise orthogonal to that. If I fit a high-degree polynomial, I'm going to start modeling the noise, where I don't really want to do that. I just want to model the signal. So typically what we would want to do is keep the degree of the polynomial small. Once you start going over cubics, you might start to get into trouble. But again, there's no absolute rules. There's no reason why you can't try to fit a high degree polynomial. It just probably is the wrong thing to do. But don't let that stop you, right? Have some fun with it. Anyway, instead of high degree polynomials, something called splines or piecewise polynomials is preferable. Even if your data actually is being generated by some crazy high-degree polynomial, it's often better to cut your sample space or your input space, say, into little pieces, and then for each of those little pieces, subintervals, say, fit a low-degree polynomial, and then attach them all together at the so-called not points. In this way, you can still model some extremely complex behavior, but you can avoid the risk of potentially overfitting. Polynomials are also quite terrible for things like trying to do prediction because they can fluctuate and then blow up rapidly. So there's a lot of issues. I mean, it's very powerful techniques, but you do have to be very careful when you apply them in practice because you can get yourself into trouble very quickly with overfitting, extrapolating, right? Which way is the polynomial going to go? Well, depending on the sign of the highest degree term and whatnot, it can shoot off to infinity or minus infinity quite fast. And whatnot. Anyway, another thing we might be interested in is, are there any weird data points in our data set? All right, so finding outliers / influential points. Because we have a big data set, n data points, whatever n is, 100, 1,000, 1,000,000, right? We might want to know, are there interesting entries, interesting or influential or outliers in some sense? Well, there's lots of different measures that you can compute. In R, you can find something called influence dot measures in R, which is going to compute a ton of numbers. And then the question is, what do all these numbers actually mean? Well, some of the most important would be, for example, the leverage. The leverage is going to be the diagonal entry of that projection matrix, PII, divided by 1 minus the entry PII. This is going to be a value between 0 and infinity. It shouldn't be 0, but it could be close to 0. It also probably shouldn't be 1 giving infinity, but, you know, nevertheless. And this is roughly saying, is my data point an outlier? But what does outlier mean? In this case, outlier in the x direction. And what I mean by that is this input to the model really far away from all the other inputs in the model, right? If we're just on the real line and we have all our data points here, and then we have one really far away, that's a leverage point, right? But again, we could be in p+1 dimensions and have a big cloud of input data points. And if we have one or more data points that are really far away from the others, they would be leverage points. In a way, linear regression is basically like computing a mean. I should say least squares regression, the least squares estimator, is a lot like computing a sample mean. And what do you know about a sample mean? Well, one really big data point or one really small data point is going to completely mess up the calculation. It's going to skew it. It's going to pull the mean away from the average. So you want to calculate the average income in a city, but then, you know, Bill Gates or Elon Musk or one of the other crazy billionaires moves in. You compute the average income and wow, it's really big, right? Because one guy just happens to have, you know, multi-billion dollars, right? And everyone else might be poor. So linear regression is more complicated than just sum up everything and divide by the total. But in a sense, it's really just doing the exact same thing, which is computing a mean. Means are affected by outliers. Leverage point is an outlier. and it can have a high effect on your linear regression. Mainly, the picture that I like to draw is something like this. If I have some data points like this, and then I have some crazy data point way out here, instead of fitting the line that I probably should fit, linear regression is going to say, oh, well, if I want to minimize the squared error, I'm going to go this way, right? And that's not what we want. So, okay, that might not actually happen in practice, but it is good to look for leverage points and just understand that they will have a strong influence on the way that your linear regression is fit to the data. All right, and we're back. Hopefully that next battery lasts because I don't have any other ones, but it is good to have a little backup here and there. Anyway, talking about different types of influential measures, we can also consider something called Cook's distance. Cook's d, or distance. And the Cook's d value, or distance, is going to be a measure of how far do our parameters change when one of the data points is removed from our data set. So it's a pretty simple question if we're looking for influential data points in our data matrix. We basically ask, how much does beta hat change when the ith entry in the data table is removed? Right? If it doesn't really change at all, then it says, well, that point wasn't very influential. If it changes drastically, like this crazy line that I drew up above with this data point out here, and the entire slope just completely changes direction, then it's a very influential point. It'll have a big Cook's distance. Now, we can compute this in many different ways. I'm going to write down the most useful way rather than, which is as a product between the studentized residual, squared studentized residual, so the sign doesn't come into effect, divided by the number of parameters times the leverage factor. So roughly, what we're saying is, if I have a big leverage, as I just noted, this means I'm an outlier in X. That is, in the horizontal direction or in the input variable, I'm an outlier. For the studentized residual, if that's big, then I'm an outlier in Y, or the response variable. I'm really far above or I'm really far below the regression plane or the regression line or the hyperplane or whatever. So roughly what Cook's distance is saying is, well, am I an outlier in one direction? Am I an outlier in the other direction? I'm going to multiply those two values together and divide by the number of parameters. Now, this is actually closely related to the F statistic and confidence ellipsoids. You can find lots of different formulations of Cook's distance, but for the sake of time and my throat, I'm not going to write them all down now. There are other measures of influence, of course, things like df betas. How far does the parameter beta I change when one of the entries is removed from the data set? df fits, how far do the fitted values change when one of the entries is removed from the data set? Something called covariance ratios, which is how much does the estimate of the covariance, or the variance, I should say, change when one of the data points is removed, right? You can just keep going down the rabbit hole here. There's lots of different influence measures. In the end, they're useful for looking for interesting points in your data set. Now, just because you find influential points does not mean you should just throw them out, but it does mean you might want to look a little closer at them to figure out, well, why are they influential, and should I continue to use them in my data set, or do I need to consider more complex modeling to account for them? Right? Because we don't want 2 points that are completely taking over the estimation problem. Anyway, moving on, we have other issues that can occur when you're trying to, let's say, build a model. How to build a linear regression model. Well, okay, we have a bunch of predictor variables, we shove them in, we try to fit a model, and we're done, right? No, because you have to make sure you pick the right variables to include in your model. The point being is that if you have two predictor variables that are highly correlated, you really don't want to include them in the model together. Because if you have two predictor variables that are highly correlated, what that means is that they in some sense have the exact same information in them. And we're just being redundant by including it twice. Now you might think, well, okay, well I'm being redundant, but who cares? The information is in the model, right? But the problem is that it's taking up two different parameters, or more possibly, but in this hypothetical example. And that leads to something called multicollinearity. It's when your predictor variables are highly correlated. When your predictor variables are highly correlated, estimation, the least squares estimator, becomes highly unstable because you're inverting a matrix with an extremely large condition number. There's like layers and layers here, but roughly it just leads to an explosion in the variances if you're not careful. And we need to have reasonable variances for our estimates in order to do good hypothesis tests and get some tight confidence intervals and confidence regions, right? Anyway, one of the big problems that you should always look for when doing linear regression is something called multi-collin, 2 L's? I think it's 2 L's. Collinearity. Yeah, 1L, 2L doesn't really matter. The point is R2 or more of my predictors highly correlated. Right? This is a problem that can occur. Now, the reason why that's a problem is basically if so, then X transpose X inverse may still exist in the sense that I can actually have an invertible matrix, X transpose X, but the inverse operation may be unstable. Now, there's lots of ways to characterize this. One way would be to look at eigenvalues. If I have a high correlation in the columns of my matrix X, then X transpose X is going to have a spectrum, is going to have eigenvalues that get really close to 0. When I invert it, the eigenvalues of the inverse are going to blow up, and that's going to be a problem, right? Because if the eigenvalues blow up, the eigenvalues that show up in that matrix are going to be directly tied into the variance of the least squares estimator. I didn't mention this earlier because I'm rambling like a mile a minute in this lecture video, but our least squares estimator, right, assuming that our errors are Gaussian, is going to be unbiased, so its mean is beta, its variance is X transpose X inverse, which means we kind of want this to be small. And if we pick our predictors very poorly, that matrix inverse is going to be really big. And that's going to be bad. Big variance, it means that we're not going to be able to detect significance in our betas because our variance will be too big. So oftentimes we want to work hard to try to correct for that. There are many ways to detect this. How to detect multicollinearity. Right, there's something called a variance inflation factor. Inflation factor. This is something that can be computed directly in R. It's basically you try to regress one of the predictor variables on all the others. So you're basically saying, how well can I predict one predictor variable from all my other predictor variables? If the answer is really good, well, that's actually bad. We have a high degree of multicollinearity. Ideally, all of our predictor variables would be orthogonal to each other, right? But you can't always get that lucky unless you're doing design of experiments, which I have way too many videos still posted here on design of experiments. But in the, let's say, in the real world, in the sense that when you don't have the ability to control your own experiment and you're just scraping data from wherever you can find it, you're likely going to have correlations in your predictor variables. As long as those correlations aren't too big, you're okay. Once they start to get big, then you run into trouble. Anyway, variance inflation is one thing that can be computed in R. Another thing is called the condition number of x transpose x, which is the ratio of the max eigenvalue to the min eigenvalue. Ideally, it would be 1, but that's just like very ideal, right? If you have an orthogonal design, you get a condition number of 1, you're super happy, right? But as long as it's not too big being highly subjective, you're going to be okay, right? Textbook authors will say, oh, well, if it's between 10 and 100, well, that's probably fine. If it's greater than 100, that's bad. If it's greater than 1,000, that's really bad. These numbers are all kind of subjective, but the point is that if you fit two models, one has a really high condition number, then you remove some variables and you get a very low condition number, you can kind of get a sense that you have removed some of this multicollinearity from your data, which is good, right, typically. But then the question is, well, which variable should I remove? So, how to fix multicollinearity? There are a couple different ways you can approach this. The first is variable selection. Variable selection can be done through a greedy search in R, or an exhaustive search if P is small, to find the best subset of x1 through xp to include in the model. Right? What we're basically going to do is try every possible, or maybe not every possible, but many of the possible submodels. We have P predictors to choose from. We're going to pick some subset. Of course, there are 2 to the P models to consider. So depending on your problem, that may be exhaustible or just, absurd, right? If you have, say, just 5 predictors, you have 32 models, you can exhaust that on a modern computer, no problem, even like a subpar one. If, on the other hand, P is 100, well, you're never going to be able to look at all 2 to the 100 models, right? I mean, the universe will die before that happens, probably. Instead, we can do some type of a greedy search, where we look at all the possible models and choose at each step. We say, let's say, which variable should I grab to put in my model? I'm going to pick the variable that gives me the best improvement, which I haven't explained what that is yet, but it gives me the best improvement. And then after I've taken that variable, I'm going to look at the remainder and say, well, which one will give me the next best improvement, and the next, until I find that no variable, the inclusion of no further variables, will improve my model. But then this leads to the question of comparing non-nested models. because if you have one model that contains another model in the sense that the parameter space of the one model is bigger than the other, that is, the parameter space of one model contains the parameter space of another model, then you can use something like a partial Ftest, right, in a ANOVA table. If you don't have nested models, you can't do that. And this leads to a couple things you can consider. In the classic linear regression setting, you can look at something called Mallow's CP value. But this is effectively equivalent under Gaussian errors to something called AIC, the Akaike information criteria. I hope I pronounced your name correctly. I'm not actually sure if Akaike is still alive, but anyway, I hope I pronounced that somewhat correct. And this is a very standard thing, the AIC, that you will see all throughout statistics, because it's really just saying, I want to minimize the log minus 2 times the log of the likelihood plus 2 times the number of parameters. And this is something very standard. Again, it has nothing really specifically to do with linear regression. AIC can be used all throughout parametric statistics. As long as I have a parametric distribution, I get a likelihood. And if I have a likelihood and a finite number of parameters, well, I can compute AIC and use it for model comparison purposes. And there's other things too, like BIC, the Bayesian information criteria, which really just does the exact same thing, minus 2 log likelihood. But instead of incurring a cost or a penalty of 2 for every parameter in your model, you incur a cost of log n for every parameter in your model. So if you have a bigger sample size, you get a higher cost for including more parameters in your model. Now, the formula I just wrote down like nothing. There actually was a whole lot of thought that went into these, so I feel like I'm not really doing it justice by just shoving them down on a notepad here and then saying, yep, just use this thing, right? There actually is a whole lot of thought. AIC is tied into the idea of like minimal entropy and things like that. I think it goes back to about the 70s or so, but I don't remember exactly when AIC became a thing. But the point is that you have all these criteria that you could use to try to optimize. In the end, all we're saying is I have a number, and this number is going to be something that I want to minimize or maximize in order to find the best model. Which one should I choose? Well, there's lots of different optimization criteria. I mean, it goes well beyond AIC and BIC, right? There's modified Bayesian information criteria. There's a DIC. I can't remember what D stands for. FIC, I think, is focused information criteria. Like, it's a rabbit hole of published papers, right? Because you come up with your own information criteria. Hey, show that it's valid in some statistical testing setting and try to publish it. But in the end, there's never really like a perfect choice for which measure to use to try to optimize over. But it might be worth considering one or more of these criteria. Now, one thing I did want to mention is that we have trade-offs here. Because what is something like AIC saying? AIC says max the likelihood, but keep p, the number of parameters, small. Right? This is something that happens a lot in statistics where we have this trade-off. Similarly, if we're looking at something like mean squared error, says we want to minimize both the variance and the bias in our model. Now, if you've ever heard bias-variance trade-off, which I hope you have, especially the ones in my class who are watching this video, right, the bias-variance trade-off is something very common in all parts of statistics because, you know, in classical statistics, you say, okay, well, I want the best unbiased estimator I can find. Great. But you know what? If we allow ourselves to have a little bit of bias, we might be able to get a big decrease in the variance. But we don't want a lot of bias. That would be bad as well. So you often get this trade-off. If I allow for a little bias, can I get a bigger decrease in the variance than I did increase in the bias? Similarly, like I said, AIC says I want to get the likelihood as high as possible, but I don't want to use too many parameters to do it, right? Every parameter is costing me something, right? So this idea of a trade-off here shows up a lot in statistics and is something that we need to take into account. And it doesn't just happen here when we're considering like the best subset model. It will also occur, right, when we do things like penalized regression methods. So another approach to dealing with multicollinearity or high dimensional problems with basically a large number of parameters p are things called penalized regression. And what penalized regression says is we're going to do exactly what we did before. We're going to find a beta hat that minimizes the sum of the squared errors. That is, it minimizes the sum I from 1 to n, sum over my entire data set, yi minus y hat I squared. But that's what we did originally. Not done yet. Because what we're going to do is we're going to add a penalty term in here, which is basically saying, don't let beta tilde get too big. So this keeps beta hat small-ish, right? So what we're going to do is we're going to try to minimize the squared error, but without letting beta get too big. There are many different versions of this. I mean, you have another one of these crazy statistical rabbit holes where you can consider tons of crazy penalties that people throw on. The two most common would be the ridge regression penalty, which looks like an L2 norm. It's lambda, some tuning parameter, the sum I from 1 to p of beta, I guess tilde is what I'm using here, squared. So this is ridge. Alternatively, we can also consider the famous lasso regression from the 90s. Ridge, by the way, I think was 70s or 80s when people came up with that. Sometimes you hear people call it, I think it's like Tikhonov regularization and numerical analysis, but I'd have to double check that. Anyway, it's an L2 type penalty. We want to minimize the sum of the squared parameters. If we do something called lasso regression, we're minimizing the sum of the absolute parameters, which you think, okay, well, that doesn't seem much different, but it kind of is. And yeah, it led to a lot of fame for its creator. And of course, a billion articles that came after that saying, hey, now we got to understand what this crazy lasso thing is and why it seems so cool. Right. Well, again, there's lots of different penalized regressions, but these are all doing the same thing. They're all trying to minimize the squared error, but keeping beta hat small-ish, right? Now, ridge regression is what is called a shrinkage estimator. Ridge is a so-called shrinkage estimator. And what that means is that, roughly speaking, as lambda gets bigger, ridge regression is shrinking beta hat towards the origin, towards 0. As a result, the variance is going to go down, but the bias is going to increase. Bias-variance trade-off again, right? All of these trade-offs are all kind of happening simultaneously. Squared error, size of beta. Bias, variance, right? The nice thing about ridge regression is everything is quadratic. And if you recall from what I said earlier, people love quadratic things because you can take derivatives, it's all smooth, there's a single critical point, and you can solve for your ridge regression estimator. which I'm not going to derive in this lecture video, but it's going to look a whole lot like the least squares estimator, but it's going to have an extra parameter here, or an extra matrix, I guess, hidden in the denominator of the least squares estimator. There's no such thing as a denominator here, but it's, right, the inverse piece here. So the point is, as lambda gets bigger, beta hat ridge will roughly get smaller and tend towards 0. I say roughly because it doesn't have to monotonically decrease to 0, but it will roughly start, lambda increasing will roughly start to push beta towards 0. The nice thing, fun fact, x transpose x may not be invertible. Ah, well, that's disappointing, right? We might not even be able to fit a least squares estimator, but x transpose x plus lambda I is always invertible. Assuming, of course, that lambda is greater than 0, otherwise this is just silly. But yeah, if lambda is greater than 0, all the eigenvalues are strictly positive. We have a positive definite matrix. We can invert that thing. And yeah, so the ridge regression estimator will always exist, even in high dimensional data when p is greater than n. It's all good stuff, shrinks to the origin, etc., etc., etc. Bias variance trade-off. Now I feel like I'm just shouting out statistics terminology, but that's roughly the idea. Lasso has, well, sadly, no closed form solution. So you might think, well, that's kind of disappointing. I can't even write down like beta hat lasso is x something 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 y. But people still really like it. And the reason they like it is because, well, what in the world does this actually mean? It means it is the least absolute shrinkage, maybe selection and shrinkage, or shrinkage and selection, shrinkage and selection operator, which is kind of a fancy way to say it will set some beta hat I to be equal to 0. Ridge doesn't do that. Ridge shrinks to the origin, and in some limiting sense, all of the beta hats will be pushed to 0. What lasso does is it will actually throw out variables from your model by just setting beta hat equal to 0. So it does shrinkage in the sense that it pushes the estimate towards the origin. It also does selection. Selection by saying, you know what, I don't really like x7, so I'm just going to throw it out, right? And there's tons and tons of actual mathematical theory that goes into this, and I'm not going to talk about any of that right now, but it would be really interesting to do in the future. And there's one quick topic I want to cover before I stop this video, and that's something called generalized linear models. Generalized linear models. Because thus far, when we talk about regression, whether it's classically squares or something fancy like ridge regression, whether we're doing variable selection or whatnot, we're always doing the same thing, which is we're basically trying to model the expected value of y as a linear combination of our input parameters, x1 through xp. Okay, great. If this is the normal distribution, with mean, say, mu, let's say yi is equal to mu I, sigma squared, then what we're effectively doing here is predicting or modeling the mean response Okay, cool. But what happens if y does not have a normal distribution? So for example, what if y is a binary random variable? It's only 0 or 1. Well, it definitely can't have a normal distribution, right? If y is strictly going to take on only values of 0 or 1, then we may want y to have a Bernoulli distribution. A Bernoulli, let's say pi I distribution, yi having pi I. That is the probability that yi is equal to 1 is equal to pi I, and the probability that yi is equal to 0 is 1 minus pi I, right? And then if we look at the expected value, we might want to model the expected value, which is pi I, and that's a natural thing to want to do. If this is a diagnostic test for some illness, like, say, cancer, we might want to know, well, what's the probability, pi I, that my subject, my patient, has cancer, given these measurements, x1 through xp. But I can't just model this as a linear combination, because a linear combination of input variables can take on any value from, say, minus to plus infinity. It's just a hyperplane. I can't give the probability of you being sick as being minus 17 or plus 23, right? That doesn't make any sense at all. So what we do is we apply something called a link function. And in this case, we use the logit link, I think the sigmoid function, or there's lots of different names here. But effectively, we try to model the log odds ratio as a linear combination of predictor variables, right? And in this case, this is, just to call this is called the log odds. And what we have here is something called logistic regression, which is a cornerstone of a lot of topics. It is a classifier or supervised learning method, and also the basis for basically all those fancy pants neural networks, right? Which basically just use nested logistic regression within itself like 50 times, and then, hey, a car can drive itself. So don't know why that works, but apparently it does. So yeah, good job, computer scientists. Anyway, yeah, this is like, logistic regression in a nutshell. And what we have here is we have a linear regression, but with some type of new probability distribution and a transformed response variable. And there's a couple main things, though. We still have a parametric distribution. And because we have a parametric distribution, things like likelihood and maximum likelihood estimation still exist, which is great, right? If you didn't have that, you couldn't do maximum likelihood estimation, but we do. And that's a good thing, because what we can do then is we can, solve for beta hat, the maximum likelihood estimator, assuming a Bernoulli distribution where pi is some function of our input variables, on a computer. Once you move away from the Gaussian distribution and move away from least squares regression, you typically don't get a closed form solution. I can't just write out a nice formula to tell you what the estimator is for a logistic regression model. In this case, a computer is going to crunch through and try to maximize the likelihood over all possible beta hat vectors, and it's going to find something, hopefully, unless the optimization fails miserably, and you're going to get your maximum likelihood estimate. Again, that is step one in statistics. Get the estimator. Then you're going to do hypothesis testing. In this case, you can't use an Ftest. No more Ftest, because the F distribution and the Ftest are highly connected to the Gaussian, the normal distribution. If we're working with a Bernoulli random variable, we can't do an Ftest, but we can do something called, or make use of something called Wilks's theorem. And Wilks's theorem roughly says, I'm not going to write it out in full detail, it's in my course notes and you can find it online if you want to know the full details, but it roughly says that minus 2 times the log of the likelihood ratio is going to be asymptotically chi-squared distributed. So if we compute the likelihood ratio, and we can do that because we have likelihoods from a parametric distribution, then we multiply by minus 2 and log it. Wilks's theorem says that asymptotically, as the sample size n goes to infinity, we get a chi-squared statistic. The degrees of freedom can be calculated based on the number of parameters in your model. I do want to highlight, this is asymptotic, and it is an important subtlety, because for classic linear regression, if some angel came down and said, yes, you have a normal distribution, then that's great. If I have a sample size of 5, if I have a sample size of 5,000 or 5 million, I can still do the Ftest. It's exact. It comes directly from the Gaussian. Granted, we don't know if our data is Gaussian, but let's just assume we do. In this case, if the angel came down and said, yes, you have a perfect Bernoulli distribution, well, I still don't have a chi-squared distribution for my test statistic. I have an asymptotic chi-squared distribution for my test statistic, and that's a little subtlety that I kind of want to highlight before I turn off this camera and go get another tea, because this thing's starting to get a little bit low. The point being that if you have a small sample size, you have to remember that your hypothesis tests in this case are only true in some convergence asymptotic sense. So if you have a very small sample size, your hypothesis test could be slightly erroneous. Doesn't mean that they are, it just means you have to be a little bit more careful when applying them. But then again, for regular linear regression, you have to be careful if you try to apply Ftests and your data isn't actually normal. So again, you always have to be a little bit careful and think on your feet when you're doing statistics. Anyway, if you happen to download my course notes, which are on my website, you'll see that I also have one page on Poisson regression. Poisson regression is basically just, I'm doing regression with the Poisson distribution, so I'm counting things. Super useful if you have a discrete counting variable. And otherwise, there's nothing that profound to say about that. GLMs is a course kind of unto itself, right? You could spend, months and months reading a textbook and going through lecture notes on generalized linear models. I have now talked about them for probably about 20 minutes, which is highly, highly insufficient. But nevertheless, the big picture, right? You have your linear regression, right? You want to predict y based on a linear combination of x. Great, you can do that. Least squares estimation. Fine, it works. Well, it doesn't always work. We have to check our assumptions. We got to check our data points, make sure everything looks good. And then we also have to look for problems like poorly chosen models. If our model is poorly chosen, we might need to select a better one. If we can't necessarily select a better one, we might want to use a fancier method like penalized regression. And if our data is highly not normal, like counting variables, or like a variable that's based on integer counts, or binary responses, then we need to get a little bit even fancier and use a generalized linear model. And the cool thing about generalized linear models is you can do all the regular regression stuff in a GLM framework. So do you want to do variable selection, ridge regression, lasso? Well, you can do that for a logistic regression as well, and then it just becomes more and more complicated as you kind of work your way into this crazy rabbit hole that is linear regression. Right, so assuming you're still watching and still with me, thanks so much for watching. And yeah, enjoy the fire hose version of all of linear regression, even though this is highly not all of linear regression. And I hope that, at least for the students in my own class, you enjoyed the lectures that I gave in person and that you were able to learn some of this stuff, and that this video was helpful for sort of refreshing some of the highlights from the course. And if you had just happened to stumble across this video by random, hopefully it wasn't too absurd and fast and that you actually were able to get something out of it. And if so, please let me know, because I'd actually be really curious to know. And with that, always remember to look at the data, because that's almost the most important thing you can always do when dealing with a statistical problem. See you next time.